Hello! In this small video, I am going to show you how we actually calculate a line integral like the integral of some vector field f dot dr. I have my little sheet of notes here. Basically, we are going to be using the formulas that are found on page 1090 in the White Stewart book. That's the 6th edition. I'm not sure what it is in the 5th edition. Sorry. It's in 16.3. So here's what's going on, first of all. We usually write the integral of some field f dot dr as the integral of p dx plus q dy. And I want to first say a couple of words about why that is the case. Basically, this is because we write the vector field f in terms of its component functions p and q. So this is the integral over the curve. F is the components p and q. And then dr is just like a little change in the position vector, right? And so we can think about decomposing that into changes in the x and the y components. So like a little dx and a little dy, put those together and you get a little dr. So we can think of dr as dx comma dy. And then we are literally just taking a dot product here. And so we get the integral over c of p times dx plus q times dy. Okay, so now the real question is, how do we take the integral over some weird curve c? So what happens is, c is usually parameterized as like some function x of t and some function y of t. So these functions x of t and y of t tell you the coordinates on the graph of c at any time t. And then we usually have some sort of range for t, like say it goes from time a to time b. And then what that looks like is, some weirdo curve that goes like whatever. Here's the values that we get at time A, and here's the values that we get at time B. And then at any particular time in between, we can evaluate this parameterization at that time, like time, 7 or whatever, that's between A and B. Just evaluate these two functions there, and then the x-coordinate is given, the x-coordinate of this point is given by this at that particular time. And then similarly, the y-coordinate of that point is given by this. So here's the deal. What we're going to do is literally just like u substitution. We are going to substitute in these things for x and y into our p and q. And then we're going to complete that by changing dx into dt and dy into dt, just like we usually do with u substitution in Calc 1. So let's see how that goes. And I'm going to switch colors here. The first thing to note is that p and q are actually functions of x and y. So if we're really being careful, we should write this as like p, the integral over c, p of x and y dx, and then q of x and y dy. And then we're going to use this fact that we are lying on this curve somewhere. That means that our x and our y coordinates are really just given by some functions of t. So we can literally substitute in x is whatever function is given in our parameterization for x of t. And also, simultaneously, y is whatever function is given in our parameterization for y of t. And then, according to u substitution, we also need to turn like dx into dt and dy into dt. That's easy enough. Dx is just going to be like x prime of t dt. And dy is just going to be y prime of t dt. Okay, so then if we substitute everything in, here's what we're going to get. We're going to get the integral of, so p, instead of being x and y, we're going to have x of t and y of t. And then this dx becomes x prime of t dt. Okay, and then similarly, q is going to be x of t and y of t. And then our dy becomes y prime of t dt. What's cool about this is that now p and q are really just functions of t. We've sort of gotten rid of all the x's and y's, right? So that means that this is really just the integral of p of t times x prime of t dt, and then q of t times y prime of t dt. And then we can think about like factoring out the dt, right? And so we just have all of this stuff dt, which looks a heck of a lot like just a regular plain old Calc 1 integral. And in fact it is. And we are going to integrate it over the range of t given our parameterization. So from like a to b, whatever a and b are. So that's the idea behind those equations on page 1090.